Hello and welcome to lecture 16 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to derive another relationship between charge and current, and that will lead to the continuity equation. Okay, so in this lecture we're going to consider a small cylinder, a box of length delta z and cross-sectional area A. We're going to place a z-axis here to label the position where the box, the cylinder begins and where it ends. So we're going to consider that it has a length delta z. And we're going to suppose that there's a flux of n particles per unit of time arriving the cylinder. And there's a flux of m particles per unit of time leaving the cylinder. So there's a current arriving, a current leaving. And in this lecture, it does not matter what kind of current that is. It does not matter if it's drift current or if it is diffusion current. All it matters is that there are n particles arriving per unit of time and m particles leaving per unit of time. And in this lecture, we want to answer the question, what is the relationship between the flux n, the flux m, and the number of particles, which we will denote with the letter P in this box, in this little cylinder. And to find this relation, all we need to do is pay attention to the physical meaning of flux. So if there are n particles per unit of time arriving, then in the interval of time delta t, n times delta t particles arrive in the box. Likewise, if m particles per unit of time leaves the box, then in an interval of time delta t, m times delta t particles leave the box. Okay, so if in an interval of time delta t, n times delta t particles arrive in the box, then the number of particles inside the box increases by n times delta t. But if m times delta t particles leave the box, so in this same interval of time, the number of particles decrease by m times delta t. So the net increase in the number of particles inside the box is just n minus m times delta t. So if this is the net increase in the number of particles, it must be the number of particles after the interval of time delta t minus the number of particles before the interval of time delta t. So this term is just the variation of the number of particles in the interval of time delta t. And we've just seen that this variation, since it's due to the flux, it must be given by this term. So this expression is just the mathematical statement that everything that arrives minus everything that leaves, it is what it stays. So there's nothing very complicated here. So that's basically the job we had to do. We had to find a relationship between particles arriving and particles leaving m and number of particles p, since what enters minus what leaves is what stays, this relationship holds. So all we need to do now is to put this relationship in a more elegant form, making a change of notation. Since flux and current are the same thing, we can, instead of expressing the flux at position z using the letter n, we can just ascribe space-dependent current, and since this is the position z, n must be the current evaluated at the position z. Now there's no physics here, this is just a change of notation. Instead of calling this flux n, we are calling this the current evaluated at the position z. And in the same way, m is the current leaving at the position z plus delta z. So using this notation, this expression is reduced to this expression. So n becomes the current at position z, m becomes the current at position z plus delta z. And the number of particles, now we're going to express in terms of the concentration of particles. So this term is the concentration, this is the volume of the cylinder, and the volume is the area times the length delta Z. So the total number of particles in the cylinder is the concentration times the area times delta Z. So we're going to use this term to express this relationship. Doing that, we just multiply everything by A times delta Z and replace P with ρ. So now we have a relationship in terms of current and concentration, which is basically what we wanted. But it's better to use current density instead of current. And if you recall, current density by definition is the total current divided by the cross-sectional area. So the total current is the current density times the area. Using this expression here, then the net flux is given by this term. And now we can just rearrange. The cross-sectional area will cancel. Delta T will pass dividing here. Delta Z will pass dividing. And we end up with this equality. Now you may have noticed that if you take the limits of the size of the box going to 0 and the interval of time we are considering also going to 0, this relationship here becomes the partial derivative of the current, but we need the negative sign here because the partial derivative would be this term minus this, and here we have the other way around. And this term becomes the partial derivative of the concentration. And we need partial derivatives because the current may also be a function of time and ρ may also be a function of space. So that's it. This is the relationship between current and concentration that we wanted. This is sometimes called the continuity equation. This is actually the 1D version of the continuity equation. The 3D version involves the contributions of fluxes on all sides. So to derive this expression, instead of using a cylinder, you can use a little cube of length delta Z, delta X, delta Y. Consider the flux in all faces, that you're going to follow the same logic. You're going to end up with this relation, which is usually expressed in terms of the divergence. So this is the 1D version of the continuity equation. And you probably have noticed that this is again a logical relationship. We're just stating that everything that comes in minus everything that goes out is what stays. But often this relationship is used to express a physical fact. And the physical fact that is expressed is the conservation of charge. So if ρ is a concentration of charge and J here is an electric current density, then this expression is telling us that the charge that arrives minus the charge that leaves are the charge that stay. So in other words, charge is conserved. And this is a physical fact, but don't overestimate the profundity of this statement. It's just a statement that whatever comes in, less what goes out, is what stays. Nothing is disappearing. Okay? And we only need the 1D version. We don't need the 3D version in our course. Now notice that this expression is very general because we did not make any assumption about the kind of particle or the kind of current. So it's valid for any kind of particle, any kind of current. But in the context of semiconductor devices, we want the current to be an electric current. So we are interested in electric current. So in our case, J will be a current in units of coulombs per unit of time per unit of area. In other words, amperes per unit of area. So if this is to be an electric current, then this concentration must be a concentration of charge. So it must have units of coulombs per unit of volume. And we're going to learn that there are two types of charge carriers in semiconductors. One type is the good old electron, but we call these free electrons because these are the electrons that can contribute to current because they can move around easily. So we are not interested in all electrons, only in the electrons that can contribute to current. So in other words, the free electrons. And we use the letter N to denote the concentration of free electrons. And we're also going to learn that there's a new type of particle, or a new type of charge carrier, that we're going to call it hole. So a hole is not actually a particle, it is an absence of an electron. But it behaves as a particle, it behaves as a charge carrier and a positive charge carrier. So a hole is a particle carrying the same charge of an electron, but with a positive sign. And we use the letter P to denote the concentration of holes. So N for negative, P for positive. So if we're dealing with a concentration of free electrons, then we can express the concentration of charge in terms of the concentration of electrons using the fact that each electron carries an elementary charge. And to avoid confusion with the sign, I'm using the magnitude of Q here. You may recall that this is the value of the magnitude of the elementary charge. So we put the negative sign explicitly to avoid ambiguity with the sign. And in the same way, since each hole also carries an elementary charge with a positive sign, then the concentration of charge carried by holes is given by this expression. Then if we want to apply this equation to electrons, then we just use this expression for the concentration, and the equation takes this form. And the same way, if we want to apply to holes, the equation takes this form when you use this expression for the concentration. Okay, so I've just mentioned that charges are conserved, that this is a physical law. Now, this law applies to the net charge, to the total charge. So if this concentration is the concentration of total charge, then this equation is always valid. But we are not interested in the concentration of total charge. We are interested in free electrons and holes. So we are interested in the charge carried by electrons and holes. And free electrons and holes are not conserved. There is a loss mechanism that makes these free electrons and holes kind of disappear. They do not actually disappear. What happens is that the free electrons cease to be free. They stop being free due to a process called recombination. So, since free electrons and holes may disappear due to this process, we need to take into account this loss mechanism in our equation. So we need to modify this equation to take into account this loss mechanism, because we want to apply it to either free electrons or holes. Now, to include the recombination process in our equation, we need to express it somehow, and this is expressed with this parameter gamma. And gamma is the proportion of particles that are lost due to recombination per unit of time. So to understand the physical meaning of gamma, suppose that P is the number of particles. So to find out how many particles will be lost, we just have to multiply P with gamma, because gamma is the proportion of particles. So when you take gamma times P, we have the number of particles that are lost out of these P particles per unit of time. So that means that gamma times P times delta T is the number of particles lost in an interval of time delta T. Now recall that this is the mathematical statement that the number of particles arriving minus the number of particles leaving gives the number of particles that are left in the box. So this is the increase in the number of particles after an interval of time delta T due to the flux. And this term is the net number of particles arriving in the box. Now, if n minus m times delta T particles arrive, but this number of particles is lost in an interval of time delta T, then the net increase is the net number of particles that arrived minus the net number of particles that is lost. So it's very easy to incorporate this term if you just recall its physical meaning. It's the number of particles that disappeared, that died, that ceased to be free in an interval of time delta t. And now we can recast this equation the same way we did earlier. But now I'm already expressing n and m in terms of the current density, and the total number of particles is again expressed in terms of the concentration. So this term here becomes rho times A times delta Z, and here is the same as before. Now we just do a rearrangement again. We divide everything, both sides, by A times delta Z times delta T. So this term cancels, this picks up a delta Z, this picks up a delta T, and we take again the limit of delta Z and delta T going to 0, and we end up with this expression. So this is still the continuity equation, but including a loss mechanism. And this loss mechanism is more often expressed in terms of the lifetime tau, which is defined as the inverse of the loss rate. So in terms of the lifetime, our equation is reduced to this form. And again, if you want to express this relationship in terms of the concentration of free electrons, we just use this expression for the concentration, and then the equation takes this form. Notice that it's positive here, negative here. And if you do the same for holes, it takes this form. Notice that we have negative here and positive here. So this is a very important equation for the physics of semiconductor devices, and we're going to use it already in the next lecture to derive a very important result that we're going to use then later on to derive Shockley equation, and that will also lead to the important concept of diffusion length. Okay, so that's it for today. Then next time we apply this equation to learn what is the diffusion length. I see you there.